All right, Gen Chem kids, we are going to learn how to use the colligative property of freezing point elevation, freezing point depression and boiling point elevation today. We're going to use it in conjunction with molality, moles per kilogram. So here we go. Let's look at the formulas here of how we calculate this. So when we calculate the boiling point elevation, the change of temperature, not the new boiling point, but just the change, is equal to the boiling point constant of the solvent times the molality. Molality is moles per kilogram, okay? So we have very specific boiling point constants for different solvents. So for example, here's a chart of them. So water has a boiling point of 100 degrees Celsius, right? It boils at 100 degrees. So the boiling point constant is 0.512 degrees Celsius per molal, okay? Benzene boiling point is 80.1. The boiling point constant is 2.53. Carbon tetrachloride has a boiling point of 76.7. The constant, though, that tells us how much it changes per molal is 5.03. Ethanol has a boiling point of 78.5 and its boiling point constant is 1.22 degrees Celsius per molal. Chloroform, 61.7 with a constant of 3.63 degrees per molal. So notice that the boiling points of the different solvents are unique. So when we're looking at the different solvents, we can't assume that they boil at 100 degrees just like water. They don't. We also see that the boiling point constants of the various element or the various solvents are also very unique. Okay, so make sure that when you're looking at the problem, you grab the constant for the right solvent. All right, so when we look at our freezing point depression, the formula is very much the same. The change of that temperature is equal to the freezing point constant of that solvent times the molarity, not the molarity, the molality of that solvent. Okay, here we have another chart with the freezing points right here of the various solvents. Notice water is 0 in Celsius. Benzene is 5.5, carbon tetrachloride is negative 23, and ethanol is negative 114.1, and chloroform is negative 63.5. Notice the freezing points of the different solvents are very different from one another. And then when we look at the freezing point constants, which is this column right here, they are also very different from each other. Water changes 1.86 degrees per molal. Benzene changes 5.12 degrees per molal. Carbon tetrachloride, wow, 29.8 degrees per molal. That's a huge amount of change. Ethanol, 1.99, and chloroform, 4.68 degrees per molal. Okay? So notice, because the boiling point is elevated, right? The boiling point becomes elevated and the freezing point is depressed. That means that the temperatures and the ranges that we have for freezing and boiling expand. So I haven't taught you how to use phase diagrams, but notice these areas where we have the liquid area actually expand when we have a solution. So we can keep whatever solvent liquid in a lot greater range of temperatures. Okay, so let's learn how we use this equation really quick. So we want to calculate the boiling point and the freezing point if I have 300 grams of ethanol and I dissolve it in 800 grams of water. The first thing we need to do is calculate the molality of the solution. So molality, if you remember, is number of moles of solute divided by kilogram of solvent. So the next thing we need to do is figure out which of these is our solute and which is our solvent. So I would say that the ethanol is our solute. Why would I say that? Because 300 grams is less than 800 grams. The smaller portion thing is always going to be our solute. And I would say that the water is our solvent. Okay, so I'm going to put the ethanol, the 300 grams of ethanol, on top. And I'm going to put the 800 grams. Let's see, I have 0.0 grams of water on the bottom. Now I need to get this top into moles, and I can do that by using the molar mass. And I need to get this bottom into kilograms. So let's work on getting our molar mass of ethanol really quick. So I've got 2 carbons, and if I look on the periodic table, carbon is 12.0. So I'm going to multiply that by 12.0. Hydrogen, I've got 6 of them, and hydrogens, if I look on the periodic table, the mass of hydrogen is 1.0. And I've got 2 oxygens, and if I look on the periodic table, the oxygen mass is 16.0. So I'm going to add all of that up. So 12 times 2 plus 6 plus 16 times 2 gives me a mass of 62 grams per mole of ethanol. Now I want my grams to cancel out here. So I'm going to put my grams of this relationship on the bottom, and I want moles on top. So I have 62 grams of C2H6O2 ethanol in 1 mole of C2H6O2. Notice my grams cancel. And I have moles on top, which is just what I want. Now let's work on getting kilograms on the bottom. So right now I've got grams. How many grams are there in a kilogram? Do you guys remember? That's right, there's 1,000 grams of water in 1 kilogram of water. So my grams of water cancel out, and I'm left with kilograms. Moles divided by kilograms, which is exactly what I want. Okay, so let's calculate this molality. So I'm going to take 300 and I'm going to divide it by 800. I'm going to divide it by 62, and I'm going to multiply it by 1,000. Okay, and once again, this likes to jump on me. I still haven't figured out why. And it's going to jump on me back. Okay, so this gives me a molality of about, oh boy, I ran into a lot of room. So 6.04. And yep, that just jumped on me again. Okay, let's head on back because we are not in acids yet. Okay, so we have a 6.04 moles of ethylene or ethanol per kilogram of water, or molal solution. Okay, so we're going to use this molality that we just calculated to figure out the temperature change by using our formula. Now, our formula, if you remember, is our boiling point constant times our molality. We need to look at our boiling point constant for water. So let's check that out. Our boiling point constant for water, right here, water, is 0.512 degrees per mol. Okay, so I have my boiling point constant, 0.512 degrees Celsius per mol, and then I need to multiply it by my molality, which we just calculated up here as 6.04. 6.04 molal. So notice our molals cancel out and we're just left with a temperature change, which is what we want. So we're going to multiply 6.04 times 0.512 and we get a degree change of about 3.096. So we're going to round that up to 3.0 degrees, 3.1 degrees Celsius, okay, with our 3 digits that we have. So that's our change. That's just the change. Now, if we really wanted to see what our new boiling point was, water boils at 100 degrees Celsius, doesn't it? We would add this change to it. So our new boiling point would be 103.1 degrees Celsius would be our new boiling point with that solution. Let's do the same thing with our freezing point, okay? So our formula, once again, is our change of temperature is equal to our freezing point constant multiplied by our molality. So let's look up our freezing point constant for water. So if I look at my freezing point constant for water, it's 1.86 degrees per mol. Okay, so here we go. My freezing point constant for water is 1.86 degrees Celsius per mol. And our concentration of our solution that we had is 6.04 mol. So our molals cancel out. We're going to take 1.86 and we're going to multiply it by 6.04. And we get 11.25. So with our 3 sig figs, we're going to round that to 11.3 degrees Celsius. Now, the normal freezing point of water, this is just our change. That's just the change. Our normal freezing point of water is 0. But remember, it's freezing point depression. So we're going to have to subtract this from 0 degrees. So 0 minus 11.3 is negative 11.3. So our new freezing point, we would expect it to be negative 11.3 degrees Celsius. Okay? Now let's take this and find the changes of temperature if the solution was made with benzene instead of water. So if it was made with 800 grams of benzene, it's still going to have the same molality. We just have to use benzene's freezing point constant and boiling point constant. So we're still having the same molality of 6.04 or 6.05 if we want to round to the correct sig figs there. Okay, so 6.05 molal solution is what I'm actually going to use. So let's look at our boiling point constant for benzene and we'll do that calculation. So let's look, boiling point benzene, here we go. We've got a constant of 2.53 degrees Celsius per mol. Okay, so our boiling point constant of benzene multiplied by our molality. So we said it was 2.53, correct? Yep, 2.53 degrees. So 2.53 degrees Celsius per molal. And our molality is 6.05 molal. So our molals cancel out and we're just left with degree changes. So 2.53 times 6.05 gives us a degree change. We've got 3 digits. That will give us 15.3 degrees Celsius that will change. Now that's just our normal change. Let's look what the boiling point of benzene is. So if we look at what the boiling point of benzene is, it's 80.1. So we're going to add that 15.3 to 80.1 to get our new boiling point. So that will give us a new boiling point of 95.4 degrees Celsius for that benzene. That's the new boiling point. Okay, let's do the same thing for our freezing point. We're going to have the same formula. We're going to have our freezing point constant multiplied by our molal. But we've got to look at our freezing point constant for benzene. So let's look at our freezing point constant for benzene. So here's our freezing point constants. Benzene is 5.12. Okay. So we have a constant of 5.12 degrees Celsius per molal, and our molality is 6.05 molal. So we're going to cancel out our molals. So 5.12 times 6.05 gives us a temperature change with, 3 sig figs. That gives us a temperature change of 31.0 degrees Celsius. Now, notice that is just the change. We have to figure out what that does to the freezing point. So let's look at our normal freezing point of benzene. Okay, our normal freezing point of benzene is 5.5. So we have to subtract that. So we're going to take 5.5 degrees Celsius and subtract 31.0 degrees Celsius to get our new freezing point of that benzene solution. So 5.5 minus 30.31 will give us a new freezing point of 25.5, or negative 25.5, sorry. Let's write that better. Negative 25.5. If it will let me write. So we have really changed the freezing point of that benzene solution to 5.5 degrees to negative 25.5. So we can really change the temperature of how things freeze by just making solutions of them. Finally. Okay, now let's write that correctly. Negative 25.5 degrees Celsius. That is going to be our new freezing point of that solution. Okay, so by just adding some solute to our solvent, we can really change freezing points and we can really change boiling points pretty significantly. Okay, have a great day. You will have some practice on doing these kind of calculations for your homework. We'll see you later. Bye.